right, so we know what vectors are. We know how to add them together. In a minute, we're going to learn how to subtract them. But how do you multiply vectors? Well, we're not going to multiply two vectors by each other yet. There's actually two different ideas that apply to vector multiplication. What we're going to do is we're going to multiply a vector by just a normal number, which is called a scalar. And the reason it's called a scalar is because geometrically, if you multiply a vector by a single number, it has the effect of stretching or scaling that vector. So, for example, if we've got a vector xy, multiplying it by a number k, you would just multiply each of the components separately by k. So if I have 1, 2, and I take that vector and I multiply it by 10, that's just like taking the 1 and multiplying it by 10, and taking the 2 and multiplying it by 10. So let's sort of see what this looks like graphically in a bunch of cases. Let's go ahead and draw the vector 3, 2. So here's 1, 2, 3, 1, 2. And go ahead and draw it rather carefully. So there's the vector c. What would the vector 2c look like? Well, we're going to multiply each component by 2. So that would give us the vector 6, 4. You might think about this as being two copies of the vector c. You could think about this as being c plus c, like move along c and then move along c a second time. But I think it's going to be more flexible to think about it as scaling, because here it feels a little bit more awkward to think about it as move along c and then move half of a c. Okay, let's do, all right, so 6, 4 is 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, so to here. And again, try and sketch it rather carefully. You know, you could actually do 3, 2, and then 3, 2. So just try and put that point halfway in between. Okay, so if this is c, this is, whoops, this is 2c. And as you can see, multiplying by 2 has had the effect of just stretching the vector by a factor of 2. What about 1.5c? 3, 2. So 1.5 is the same thing as 3 halves. So 3 times 3 halves is 9 halves. And then 2 times 3 halves is 6 halves. Let's go ahead and write that in a decimal notation. So this would be 4.5, and this is 6 over 2 is 3. Okay, so 1, 2, 3, 4 and a half. 1, 2, 3 would be right here. Okay, so this is 1c, and then we've gone another half c. So this is 1.5 c's. So we've stretched the original c to be 1.5 times as long as it used to be. But notice they're all facing in the same direction still. Okay, what about negative c? Well, that's the same thing as saying negative 1 times c. So what that does is that reverses both the x and the y. So what does the vector look like if you reverse the x and the y? Instead of going right by 3, now you're going left by 3. Instead of going up by 2, now you're going down by 2. So it looks like this. So this would be negative c. So a great way to think about negative c is it just reverses the direction of your vector. It's still the same length. It's just that instead of pointed this way, now it's pointed the opposite way. All right, let's do last one. This would, multiplying by negative 2 would both reverse its direction and scale it. So we'll do the multiplication. 3, 2. So this is negative 2 times 3 is negative 6. Negative 2 times 2 is negative 4. And so now I'm going 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. And so I got that, oops, that vector there. So it should go through this middle point, which it does if I make the point large enough. All right, so this is negative 2 c's. All right, so the reason we took all this time, obviously you can do this numerically. It's going to be really, really helpful to be able to imagine it geometrically. When you see a vector and you see a number, just imagine, oh, I've stretched the vector to be that much longer. When you see a negative in front of a vector, you think, oh, I've flipped it around the other direction. Let's see how this plays out when we subtract. Actually, let's do another video.